In this video, we're going to discuss a trickier skill of not only solving rational equations, but writing them first from a verbal description. So when we say rational equations, they're going to look something like what you see here over on the left, but the types of word problems that they're going to come from might involve some of the following topics that you see popping up on the screen. For example, you might be in a split work situation over some period of time. Maybe you and some other people are mowing lawns together, and how fast could you all collectively mow one lawn at the same time if we know how fast you individually mow one lawn by yourself. Another situation is maybe you are traveling via boat, and when you travel on a boat, there's usually a current in the water. So when you're traveling one direction in that boat, you're going to have your own speed, but the current is going to either be working with you or against you. And then in these situations, you're usually traveling back in the other direction, meaning if the current was working against you, when you travel back, it's going to work with you. And then lastly, you might see a situation involving going uphill and downhill on perhaps a bicycle. If you are biking uphill, your overall speed is going to be slower because it's a little harder to go uphill as opposed to going downhill when gravity would be helping you in these situations. So ultimately, the challenging piece of this lesson is taking a verbal description and writing down what you're going to be setting up for your equation. And once the equation is set up, then things are pretty easy to solve. So let's just go ahead and jump into the first little bit of this that you need to know, which is something very relatable. Hopefully in your past, you have come across the original equation for D equals RT, distance equals rate times time. A very common enough formula that you're hopefully familiar with. If, let's say, you were traveling on the highway at 60 miles per hour and you're traveling for 2 hours, then your overall distance traveled would be 120 miles. So it's just a multiplication situation. But what you're going to relate this to is rational functions, where you have a denominator. And a big thing to notice from this first slide is that time is the common thing that you are basically solving for in many of these problems. So you're going to want to get time solved for on one side of the equation, which if you take the D equals RT original formula and you divide both sides by R to cancel out the R on the right, well then T is now going to be all by itself, and then distance divided by the rate is what's going to appear on the other side of the equation. So basically, time is going to equal the distance traveled divided by the rate. And this goes back to what you saw on that very first slide. The distance is talking about how far you're traveling. The rate is your speed, but your speed moving by yourself, or the rate that you complete something by yourself, or without the current, if let's say you're a boat floating in the water. And then T, your time, is going to be the total time the entire job is taking. Because again, this is a situation that helps you answer the question, if you and 3 friends are mowing yards together, you can mow the yard at a certain speed individually, but if you were to all mow the yard together, what would be the total time that it would take? And the same thing would be the total amount of journeying that you would be doing. If let's say you're biking somewhere to and from, or you are on a boat somewhere to and from, time is what the amount of time it takes you doing something together. All right, enough talking. Let's just go ahead and get to some practice problems and take it from there. Keith and Jeremy mow yards on the weekend. They can each mow a single yard in 0.75 hours. John wants to join their yard mowing company and can mow a yard in 0.5 hours. Write an equation to show the amount of total time it would take all 3 of them to mow a single yard at the same time. So let's break this problem down and let's look at our individual concepts of distance and rate and time. The distance in this case is 1 yard being mowed. It says that in the beginning. Jeremy and Keith, they each can mow a single yard. They can travel the distance of 1 yard. They can invest the amount of yard mowing power for a single yard, and that happens in 0.75 hours. So the distance that we're traveling in this case, the unit of distance is 1 yard being mowed. The rate, in this case, is the amount of time it takes them working by themselves. So again, you can see in the beginning, Jeremy and Keith mow a single yard in 0.75 hours, and rates are supposed to be set up as a fraction. So 1 yard is over 0.75 hours. That means 1 yard per every 0.75 hours. And that works for Keith and for Jeremy. But it says in the second sentence that John mows a single yard in 0.5 hours. So John mows the yard a little faster. 1 yard over 0.5 hours. That's the rate that John is working. Lastly, the time of them all working together, well, that would be the amount of time it takes them to mow 1 yard at the same time, but we don't know how much time that's going to take. That's where the variable comes into place. We don't know. We know individually it takes Keith 0.75 hours. It takes Jeremy the same amount of time. And then John, it takes him 0.5 hours. Well, okay, that's individually. But if they're all working together, it's going to take them some unknown amount of time, X hours, but they're still just mowing 1 yard. The overall distance being traveled, the numerator in this situation is 1 because the distance is 1 yard. Let's just go ahead and set things up, and then hopefully that will give you a little more clarity. You can make Keith his own fraction of 1 over 0.75, Jeremy the same thing, and John going a little faster with mowing the yard, 1 over 0.5. All of them adding up their contribution to the work together, adding all that together, they are going to mow 1 yard in X hours. We don't know what X is. We don't know how fast they can mow the yard working together. That is what it is now asking at the end of the question. How long does it take all 3 of them to mow a single yard at the same time? So hopefully this makes some sense. It relates back once again to time equaling distance over the rate. However, there is no single number on the other side of the equal sign. We simply know that all 3 of them have their distance over rates, their rate that they're mowing the yard, and all 3 of them working together, they are going to mow 1 yard in X hours. And we don't know what X is yet, so that's where the solving piece now comes into play. And also keep in mind, this is the first example meant to introduce you to the concept. If you still don't fully get it, that's okay. There are a couple more examples that are going to pop up. So let's now solve what we have here. To keep things simple, we can just go ahead and take these fractions and turn them into decimals, and then adding everything together, you're going to get 4.6 bar. Multiplying both sides by x gets that x out of the denominator, and then you would ultimately divide both sides by 4.6 to get x all by itself, and then 1 divided by 4.6 bar is going to give you approximately 0.21 hours, which hopefully makes sense intuitively. Because if all 3 of them working together, you would assume they're going to finish the job faster if individually they were at 0.75 and 0.5 hours of mowing 1 yard by themselves. If they all work together, then they should logically be doing it way faster. So 0.21 does make sense. Let's take a look at a second one. You and your friends are going to take an 8-hour canoe and kayaking trip in the Everglades. From the dock, you will be traveling 5 miles upstream and then 5 miles back downstream. On average, your speed, without accounting for the current, is 4 miles per hour. When you travel upstream, the current will be working against you, meaning it's going to slow you down. And when you're returning downstream, it will be helping you. The current is going to increase your speed. Write and solve an equation to determine the speed of the current. Let's jump right into it. This problem's a little different. You are now being told the total time of your journey, your entire trip, is going to be 8 hours. You're going into the Everglades and then you're coming out of the Everglades. And it says the entire trip is 8 hours long. So you know the total time in this problem, unlike the previous example. The distance you're traveling, you need to think of it as two parts to the situation. You're going 5 miles upstream and then you're turning around and then 5 miles back downstream. So there's going to be two pieces, two rational components of this equation. Lastly, your rate. It says 4 miles per hour without accounting for the current. So by yourself, you canoe or kayak 4 miles per hour as your speed. But then with the current, you need to think of the current as slowing you down or speeding you up. That's why it says plus or minus c. The current could be adding to your speed, so 4 plus c, and the current could be slowing you down. So that would be 4 minus c. So let's take a look at what things will look like. 8 represents the total time of the trip, and then 5 is the distance, and that would go over the rate of you going against the current. It doesn't matter which one you do first. You going against the current would be 4 minus c. Relate it back to time equaling distance over the rate. The distance traveled upstream, you are going 5 miles, and the current is working against you, so it is slowing down your 4 mile per hour paddle. We don't know the speed of the current. That's what we're trying to solve for. We don't know how much the current is slowing you down and speeding you up. The current is a constant thing. It's either helping you or hurting you. It's the speed of the water without you doing anything. And the second piece of the rational function you can see when you're going downstream. You're traveling 5 miles. And since the current is now helping you, your rate, which again, 4 miles per hour by yourself, your rate is now being increased by the current. So that's why it says 4 plus c. This is the most important part of the problem because this is how I am justifying the setup of this function. I have tried to give you a relatable concept of distance equaling rate times time, but this is not a rational function. There's no fraction piece to it. So we solve for t by dividing both sides by the rate, and that allows us to have the formula of t equals d over r, which we have used for the last two examples and we will use for the third one. But let's now go ahead and finish solving this, which we have practiced as a skill in previous videos. So I'm going to do this kind of quickly. We need to now multiply both sides by the common denominator. And the common denominator, in this case, uniquely, we have a 4 minus c and a 4 plus c, and then that 8 only had a denominator of 1. That's not a unique denominator that's going to change anything. So the overall common denominator is 4 minus c times 4 plus c. And if this is happening too fast, then just refer to my previous video where I explain the common denominator concept a bit more. We are then going to multiply both sides of our equation by 4 minus c times 4 plus c, and that is going to allow us to cancel out a bunch of stuff and use some distributive property and multiplying of things back together. It would be important to notice that the 8 did not have anything in the denominator that was going to cancel with our 4 minus c times 4 plus c. It is only the second and third pieces to this equation that have denominator chunks that can cancel out with our common denominator. The 8 is just going to distribute after these binomials are multiplied back together. There's a little bit of Algebra 1 for you right there. Hopefully you're able to keep up, and here is what things would look like. Putting the 4 minus c times 4 plus c back together gives you a trinomial, 16 minus 8c minus c squared, and then the 8 would just distribute to it. And on the right-hand side, we have some like terms to combine. Distribute the 8, set everything equal to 0 because it is quadratic. And then from here, you could jump to the quadratic formula, or you could factor out a GCF of 8. It doesn't really matter, but this is a quadratic formula problem, and that is what you would need in order to get the answer of 1.19. And if you use the quadratic formula correctly, then you would also get a negative answer, which would not make sense because the current of a lake or a river, whatever, that is a positive effect on you. It is not a negative value. So anything negative in this case would be an extraneous solution. But 1.19 miles per hour makes perfect sense. The Everglades is a wetlands area and does not have a very fast current, so this absolutely makes sense intuitively. 1.19 miles per hour is the value of that current. All right, so we have now done a couple of these problems, and they are a little involved, so it is time for you to take a shot at reading one to yourself and seeing if you can correctly set things up using distance and rate and time and taking into account the reading. So I will let you read this to yourself, and you can see that I already highlighted things. And keep in mind, this is a slightly elevated example because the little twist right here, I'll go ahead and highlight that in green. Scotty's return journey home is taking him 2 hours longer, and that 2 is going to have to be factored into your equation somehow. So I will let you pause and work with that, and on the next slide, I'll break this problem down a little bit for you. And all right, here we go. So the distance traveled is 12 miles downhill and then 12 miles uphill. The rate when Scotty was going downhill is x. We don't know his downhill speed. It said that at the end of the equation. But it says it slows him down by 8 miles per hour if he is going uphill. So that is why x minus 8 is his uphill speed. Now we can begin to set up our function. We know that distance over rate is going to equal time. So we know that 12 miles downhill, he was traveling at some rate we don't know, but then uphill, 12 miles is how far he was going, but he was 8 miles per hour slower when biking uphill. But now the thing is, it says his uphill speed, his uphill time is 2 hours more than his downhill time. So that means you take the downhill expression, which was 12 over x, and that amount of time is going to be added by 2 for 2 hours, and then you will have it equaling the amount of time it takes him when he's going uphill, because going downhill, you're going to be moving faster. Uphill is slower. So however much time this takes, you would just be adding 2, and that would be equivalent to his uphill journey time. I would say a common misconception to this is you might add 2 over here and not over here, but keep in mind he is moving faster right here, and then this is slower. So to account for his slower biking speed, you would be adding 2 to the faster time, because adding 2 hours to something that was already fast is going to slow it down. And I might be throwing you off a little bit by all of this talking, so I'll just let you stare at it and you can make sense of it, and I'll just let the rest of this play through for the solving piece. And then once you have that common denominator, you can start canceling things out, and then use a little bit of factoring or quadratic formula, and you will get your 2 answers. But the negative answer would not make sense because you would not have negative speed. Like you traveling, or a rate of you biking is positive, not negative. So 12 miles per hour downhill was his speed, and when he was returning uphill, he was only traveling at 4 miles per hour, which does make sense. If you're going uphill, that's a lot harder. Thank you for watching the video. Drop a comment if you have any questions, and I will see you next time.